no, the ship is about to crash. We have to stop it now. And only seconds to go. Boy, is it a good thing that we got that ship stopped. Welcome to today's walkthrough as we go over the lab of torque. Now, in this lab, we're going to be basically studying the conditions for static equilibrium. Okay, but before we dive in a little bit deeper on that, let's take a look at this week's PreLab activity. In the PreLab, we're going to go into the interactive simulations with PHET. You see the balancing act has three options. The intro, we have the balance lab, there's the game. We're going to go for the balance lab. Double click on that to bring up the workspace. As you can see in this workspace, you have the show option, you have the position options palette, you have the bricks available to you. You have these two supports on this and a toggle down below to change setups. So we click on the toggle. So we do not have the supports. We don't want the supports in this case. We don't need them. Let's turn on showing forces from objects. We're already going to see the mass labels, how much mass each object is. And we're going to turn on the rulers. It may make more sense for you to look at marks. Whichever is fine. We'll leave it on marks for now. Grab two masses of different sizes. You'll want a minimum of 3 masses for your experiment. You'll find that this does not balance out. So you shift things around until you find a spot. You know that the larger mass should be closer, so we'll shift that to a different position and play with it until you finally get them balanced. Once the system is balanced, you take a screenshot and you'll make sure to calculate the torque of this mass, the torque of this mass, and all the other masses you have on that workspace, and you'll calculate the torques of each of those masses, sum them up to make sure that they add up to be 0 and that this in fact is in static equilibrium.
So in recent weeks, you've covered not just linear motion, but you've begun to explore a different type of motion, which we refer to as circular motion. And circular motion is a special case of motion through a curved pathway. But now that we have these two, we've opened up a new possibility, the possibility that an object that moves will not just move through space in a circular pathway, but parts of it may move in a circular path around another part of that object, which we refer to as rotational motion. So now linear motion corresponds to the translation through space of the center of mass of an object that's now bulky. We're no longer just thinking about point particles. And now you've been introduced to circular motion, where we have change in position, theta, omega for angular speed or angular velocity. We're going to use those words kind of interchangeably now. And then we have angular acceleration represented by the Greek letter alpha. And just like we did, when we finished talking about motion and kinematics, we started talking about the causes of those motion, namely forces. And so now we turn our attention to the forces that cause circular motion and rotational motion. So we start out with Newton's second law, and we say, okay, well, we want to remember to some extent that these are vectors, so we'll write that in this case. And we note that we have this force applied to this body at some point that's not along the center of mass, some distance from that center of mass, which we refer to as the radius. And so this force at that radius, we want to multiply our force by radius. But remember, radius is a vector here. So we want to multiply the force by the radius. We can't just throw those two together and call it a day. These are two vectors, and that direction characteristic is important. So we write this multiplier here, which we call the cross product, and this type of multiplication we'll discuss in live. But we multiply radius times force, and over here we will multiply it times the acceleration. Now, we're going to kind of do a little cheat here, because once we get into circular motion, because it's kind of a special case of motion along a curve, we're going to do a little cheat and just follow the vector results that come on this side. And over here we're going to focus just on the R and A. We say, okay, well, the tangential acceleration is, if we recall, r times angular acceleration. And we rearrange that and substitute that in. We get this quantity here, mr squared, which we'll talk about in the next lab, and this alpha, which is the angular acceleration. And on the left-hand side, we see, oh, okay, well, this has got an angular acceleration, so we've got some force-like quantity that's causing angular acceleration. This must be some force-like quantity here that's causing that. And we're going to give it a new name. We'll call it torque, which is a Greek letter, it's the T in the Greek alphabet. And as a matter of theory, we then write, okay, well, the torque is defined as the radius at which the force is applied crossed into the force that's applied to cause the rotation. As a matter of practice and in your homework, you will write torque RF, the magnitudes of those vectors, sine, and the angle between those two vectors. We'll talk a little bit more about this when we go over this cross product concept. And so one thing that we can do with torque is now we can bring this concept of, again, static equilibrium that we use for the force table, we can bring it into this situation for static equilibrium for something that could rotate. And here we are, there's our familiar friends, and welcome. We've got a new one. So now when you work out these problems that are static equilibrium for something that can rotate, you start out with the sum of torques, summing to be equal to 0. Again, this is Newton's first law for a rotating body, and then Newton's first law for a translating body moving through space. We start with this one, and as it becomes necessary, you look at your translational, your x and y direction bits. So when you're working on this lab activity and you are ready to start drawing your system in the free body diagram, there are a few things to just be mindful of how we're expanding this over what we did for previous stuff. This is very similar to the lab where we did the force table, but in this case the vectors are a little bit more spread out and maybe a little bit less confusing to try and navigate. So consider a situation where we have a straight object that has a mass, a non-zero mass, and it's balanced on something that some fulcrum, and is a box on one side, and a man or a woman or anybody walking or standing at one other point, and you have a third person hanging from this object over off to the side. And even in some another situation, if we have something that's pulling at some non-perpendicular angle. So when you draw your free body diagram, you'll say, oh look, some extra movie magic there. When you draw your free body diagram for this, you want to be more careful about where we place everything, but you do want to make sure you have everything in place. So we write down just a straight line for this board, and then we put like a mark of some sort, a dot or a circle or something like that, just to mark where everything is relative to each other. You indicate your forces according to what you see, and then you indicate a positive angle of motion. Now this is static equilibrium. It's not going to move, but it could move if we change the forces somehow or cut something or whatever the case. We want to give ourselves a positive reference. And so indicating this around the pivot point is helpful to remember, okay, which forces are going in the positive direction and which forces are going in the negative direction relative to your indicated locations. You also want to indicate your radius from the pivot point that you've designated to each point where there is a mass or some force acting on your system. Now your D2L should have a PDF document on there, which is not currently meeting accessibility, and I apologize about that, but it does have two examples of the same problem worked out with a pivot point at a kind of a natural location and then a pivot point at an arbitrary location. Look through it so you can kind of get a sense that if you're careful with your relative radii to each force from the point of pivot that you've chosen, that it still ends you up at the same place. So just keep that in mind.
The equipment for today's lab is pretty straightforward stuff. Basically start out with a meter stick that has centimeters and millimeters graded on one side. In addition to the meter stick, you'll have 3 to 4 hangers whose design is to be able to slide up on the meter stick. In addition to which is the fulcrum clamp, which also is able to slide on there. You'll notice that there's a screw here. Fix it on there. You just simply slide it upon. Once you've measured your meter stick independently, it would be unwise to assume that just because the meter stick is nice and balanced and straight and everything, that the center of mass of this meter stick is exactly at 50 centimeters. You want to make sure that you do a very accurate balancing test on your fulcrum in order to confirm that this is exactly where the center mass is. You may have to adjust it accordingly, a little bit at a time, to confirm that it's at the center of mass. The meter stick is going to balance upon this stand, which acts as a fulcrum, along with the wings of this. Make sure that you set it so that the screw of the center mass, you won't do this with the hanging clamps, but you'll want to hang this meter stick upside down so that you have more stability. And as you can see, this one is not balanced right at the center. Finally, you'll be using hanging masses that you've used in previous labs that go from 1 kilogram all the way down to 10 grams. Now, we won't be using such heavy masses. We're going to stick in the 100 to 200 gram range, but these masses will be what you'll be using for this lab activity. When you first begin, what you'll do is you'll place the meter stick's fulcrum into the support and check to see if it's balanced. If it's not, you just simply take this out. It's clearly heavier on this side. There's more mass on this side of the meter stick pulling it down, so we shift it a little bit to the left to put more mass to the left. Give it a little bit of a nudge. See what it does. Keeps acting the same way, so we need to put more mass over there. Keep on doing it. Don't go too fast at a time. See, it seems to be settling in on this spot, so that may be a little bit too heavy on that side. We'll bring it back this way just by 0.5 millimeter. That seems good. So we tighten it gently. Tighten it gently and put it back in place. Make sure that there's no rubbing against surfaces. If there is, change the equipment for better equipment. Once gentle tightening, it should stay fairly balanced. Once it's balanced, you slide on your first hanger to 15 centimeters, and you're going to place 100 grams of mass upon it. So you set this object on here, but you also want to slide on your second mass. So you want to slide on your second hanger clamp and get it ready to be moved around. This one you want to have fairly fixed. Make sure you align the edge with the measurement of interest. Set that down there. Clearly you've got more mass over there. That clamp is pulling it down. Now we're going to make it more heavy with that 100 grams. Bring on your 200 grams, slide it into place. Now be careful here, because you don't want to just again presume that your center of mass is 50 centimeters, and so you take this radius exactly as you expect it to. You want to subtract from the measured center of mass that you've got from balancing the stick and determine this by subtraction. So you move this inward, you see how it goes, see how it's kind of getting a little bit more balanced, so you don't want to go too big a jump. Give it a little bother, see if it comes back to center. Give it a little bother the other way, see if it goes back to center. Seems to be balanced. You tighten that down, and you make your measurement. You'll repeat the process for a third hanging mass, calculating percent differences. Do we want to use percent error? It's a question you want to weigh and put amongst yourself. Finally, you'll try to determine where the pivot point should be, such that you have a hanging mass and only the meter stick arm hanging out, such that the force of gravity is pulling on the center of mass of the meter stick. So you adjust this until you start getting balance, so you can adjust it, and you start to see that there is actually a little point. Don't try to use my numbers. Make sure that you discover your own with your own equipment. You want to ask yourself, why do you suppose these wooden sticks, why not are they uniformly massed? And once you're reasonably satisfied that you can balance your meter stick, with just 100 grams on one end, you mark your pivot point and calculate your percent differences of what you expect it should be versus what your sum of torque should be, hanging mass, center of mass, around that fulcrum. Once again, be careful that center of mass is now change. This is your fulcrum. The center of mass is now the radius difference between these two positions. And this radius is now this difference. So you have to be careful. Okay, well, that's it for today's walkthrough. It seems a little bit quicker than normal, but don't be fooled. This can be a real pain in the neck trying to get them to get into static equilibrium and confirm that's exactly what you have. In the meantime, I think I'm going to go ahead and use some torque and put this boat back in action. And see you in the lab. Well, hope you enjoyed. Dang, I keep doing that. I hope you guys enjoy these pre-lab walkthroughs. I can't even say the thing.